Okay, good morning. Before I start, let me just get a sense of the background of all of you. So I'm right in assuming that all of you are from computer science, right? Yeah. Have you had any courses in statistical physics during your training? No, none of you. Okay, good. So what I'll be talking about over the course of the next 4 lectures is how do you actually use a completely different perspective than what you might have been introduced to so far on understanding networks. So networks is like, the proverbial elephant. Uh, all of you know the story of this elephant and the 5 or 6 blind men, right? So they came to see an elephant and someone touched the trunk and said that, this looks like a pillar. So the elephant is like a pillar. Another touched the tail and said, it's like one of those like brooms. Another touched the, like a broad shoulder and said, oh, it's like a wall and so on. So different perspectives always have different ways of illuminating aspects of the same subject. And so what I'll be talking about is a completely different perspective, that of statistical physics or statistical mechanics for understanding networks, which hopefully will give you a new set of tools. So we all need tools to understand uh, a system that we are unfamiliar with. So hopefully this will give you a completely new bag of tools to attack problems related to network science. So the first lecture would actually deal with what exactly does statistical physics or what exactly does physics have to say about networks, which other areas probably won't share with it. And let me at the very outset encourage you to ask me questions anytime you feel that you feel that I'm not being very clear about it. So don't just stop and think, okay, maybe I will ask at the end of this thing, because none of us wants to appear as foolish to our peers, and so we tend to think that, okay, this is probably too stupid a question. But believe me, usually what happens is that everybody has the same question, just nobody has the courage to ask it, and so everybody's thinking everybody's much smarter than me, and so you end up nobody asking the question at all. So believe me, if you don't understand something, chances are that at least 50% of the other students also are not understanding it. So in that way, I will actually know that I'm probably skipping ahead too fast, or maybe I'm not being clear. So please feel free to stop me at any point and ask me to clarify. All right? Okay. So the first lecture, as I mentioned, is about the what and the why of physics and network science. So let me ask, suppose you are asked to build a complex system. Let's say you are asked to build a human being. Okay, how would you go about it? So first of all, I need a count of the component parts. You want to build or you get a DIY kind of kit for building a cupboard. Okay, so you get this set of components, right? So right there you have the component list. Okay, so to build a human, a typical human, you need so many cells of various types. Considering the fact that we make a fetish out of muscle bound hulks, actually muscle cells consists of only about 0.001% of the typical human body, okay, including Arnold Schwarzenegger. So most of our cells are actually this erythrocytes. Then the skin cells make up about 0.5%, bone marrow cells make up 2.5%, platelets 5%, and so on. Now you notice that neurons don't get a mention at all. So we pride ourselves on our brains. The human species are supposed to be so much smarter than all other animals. neurons don't even make up, actually muscle cells make up more of our body than neurons, which tells us something, right? So, so anyway, so this is the parts list, but suppose I give you a DIY kit for building your cabinet and I give you just the parts list. You'll be stuck, right? Because you also need to know how to put it all together. Okay? So the next thing that we need is some instruction about how to put up all these cells. So this is the recipe for a human being. Okay? So you have the ingredients: 35 kg oxygen, 6.4 kg hydrogen, up to 1 milligram cobalt. Now, is it that you just collect all the component parts and you put it in a beaker and shake well and out comes something like that? Not quite, right? So you need obviously some fairly detailed set of instructions to put it together to get something like this, right? So the first thing that we who are physicists work on network science, why we get into network science in the first place is we realize that it's not enough to know these component parts. We also need to know how exactly to put them together such that the components interact with each other in the correct way. Okay? So then, how do you write this instruction set? Okay? How do you say, okay, in this case of the DIY kit, you have this instruction that first take this big piece of board, then you screw in this large piece of plank of wood that you see, then take these screws and put it together. So that's basically a detailed set of instructions about how the different parts interact with each other. And that's precisely what we need in any complex system. So how do we describe these interactions? In the case of the DIY instruction kit, you don't really think of it as a network, but actually, if you really think deeply about it, it's nothing but a set of instructions about how to set up a network. Okay? Now, that's not typically the way we think about a piece of furniture. We rarely think of a furniture as a network, but it is, okay, if you think about it that way. And the advantage of thinking that way is that now I can not only describe this particular piece of furniture in that language, I can also, describe this in terms of exactly that same language. Okay, so we use the language of networks to describe these interactions between the set of components that make up any system. Okay, and typically we will deal with complex systems. Okay, so I'm sure you know this very well, but I just put this for completeness so that we know that we're talking the same language. So when I talk about networks, I essentially mean a system which is described by a set of nodes or a set of vertices and a set of links or edges. So from a actual system point of view, these nodes or vertices basically represent the components and the links or edges represent the interactions. So you have pretty sure that you have seen this. So typically, when a mathematician writes it down, he will say that a graph is described by a function of V, which is the set of vertices, and E, which is the set of edges. And this basically is the network. All right. So when I say nodes, what I mean is that it's equivalent to what mathematicians would call vertices. And when I say links, again equivalently it's edges, and networks are used equivalently as graphs. Now, we can represent a network using a graphical representation. So for example, we represent the nodes as basically ellipses which are properly labeled, and then the nodes which are basically interacting with each other are connected by lines which essentially represent the links. But of course, working with this is very difficult. You know, if you want to, if you have a very, very large network, let's say even a 1,000-node network, you know, a graphical representation would be very confusing. And certainly you can't do any mathematical operations. If you want to run a computer program to find out various interesting properties of it, this is pretty much useless. So an equivalent representation of the network would be its adjacency matrix. Okay, so an adjacency matrix, as you know, is given by the definition, would be one in which the ijth entry of the matrix is 1 if a link exists between I and j, and it's 0 otherwise. So if you notice, this picture and this picture are actually the same. So if you look at A and B, the corresponding entry, the eighth row and bth column, has an entry 1. Then A and C doesn't have a link, so the corresponding eighth row and cth column has 0, and so on. All right. So these two representations are just equivalent. Okay. Just, you know, which one is more convenient? So you might say, okay, then why don't we just work with matrices? Why even work with you know, the graphical representation? That's because the human eye is a very good pattern discriminator. You know, so far we haven't come up with a algorithm which is even equivalent to the human eye. So if you look at a network, sometimes patterns pop out. If you look at its graphical representation, patterns pop out which then you can try to quantify using the algorithms that you have. But the human eye is actually the first thing that you use to quickly eyeball are there any obvious patterns in the network. So that's why sometimes we use this graphical representation. But of course, it becomes more and more difficult as you go to larger and larger number of nodes. All right. So this question of why study networks may not sound like a, you know, it sounds like a no-brainer these days when network science is, you know, kind of on the ascendancy. But for a long time, you know, this question about why should we even bother to study about networks was actually a, you know, question that puzzled a lot of people. And Philip Anderson, a Nobel Prize winning physicist, back in 1972 wrote this wonderful paper called More is Different. It's not a paper, it's like more like an article. You can all go and read it. It's a wonderfully written article where he argued, why do you need a science of networks? Well, he didn't call it a science of networks, he called it the science of emergence, but it all boils down to the same thing, where he said that you know, suppose someone is giving you this argument that, look, in the end everything is made of atoms, and atoms are made of electrons, protons, neutrons. Electrons, protons, neutrons are themselves made of quarks and gluons. So actually we should all do string theory, right? I mean, if we really want to understand the universe, there's no point in trying to study, let's say, computers or studying this, because in its most fundamental essence, everything is quarks and gluons and maybe strings. So, and some of my string theory colleagues actually still, you know, persist with this kind of argument that string theory is the only thing worth knowing because everything ultimately is strings. And Anderson gave a wonderful counter argument to that. He said that, look, yes, you can always find you know, a pair of sciences such that the fundamental entities of science X is governed by the rules of science Y. So for example, if you look at you know, a material, so which is the domain of solid state physics. So solid state physics looks at the properties of metals and semiconductors, and what constitutes these solids are of course electrons and other particles, and these are themselves studied by elementary particle physics. So the fundamental constituents of the materials obey the laws of particle physics, but particle physics cannot explain aspects of why are metals conducting, for example, and semiconductors, you require some doping in order to make them conducting? Or why do you have superconductivity? So particle physics doesn't have any answers to that. And that's because the phenomenon of superconductivity or phenomenon of the doping of semiconductors, making them able to behave as transistors and diodes and so on, this is something that emerges at the level of the larger system, at the level of the solid. It doesn't exist at the level of the elementary particles. He took examples from the other end also. So he said that, look, psychology studies human behavior. Now, of course, if you think that human behavior is primarily the effect of the nervous system obeys the laws of physiology. But a physiologist would have very little to say about human behavior. I mean, certainly you wouldn't go to get diagnosis for some mental issues to a physiologist. You'll go to a psychologist. Why? Okay, because in the end you can always argue that the brain obeys the laws of physiology. So why not go to a physiologist? That's because when all of these 10 to the power 12 neurons are working with each other, they create phenomena which essentially is outside the arena of experience of a physiologist. A physiologist can maybe tell you about what's happening at the scale of a single neuron, maybe even at the scale of tens of neurons. But once you have, this whole billion or, I think 10 to the power 12 is more like a trillion. So this trillion neurons working together, you have this very crazy behavior of a human person, which a physiologist will be, completely at the wit's end to explain. And then finally he said that, look, social sciences, which deals with crowds of individuals, each of these individuals is, of course, falls under the domain of psychology, but the crowd will follow behavior which you cannot explain using the laws of psychology. Case in point, well, we have all heard of riots, right? So typically, if you look at the individuals who make up these rioting crowds and you go and interview them after the event, you'll find that probably they are all very reasonable people holding, very moderate opinions. But somehow the same people basically engaged in looting and arson at certain points of time. So I have a personal experience. I was on a train ride somewhere and we were going through some part of a particular state. I won't name the state. And some college students got up on the station from some of the station, and then over a very minor matter of whether this person is going to have a seat or not, a fight ensued in the train between the students and those who were on the train, and the students actually behaved abominably. So after things calmed down a bit, one of them sat beside me. And we just started talking, and it turned out that he was studying mathematics at the local university, and then we really got into a very nice discussion. And at the end, he wanted to know from me, okay, what book should I use to learn these topics and so on. He was taking down notes and so on. Then how do I apply for graduate school? Can I get into your institute and so on? So after all this, when he was about to get down, I couldn't resist myself asking, you seem like a very, very smart and intelligent and kind person. Why did you engage in this behavior? And he was so ashamed. He didn't really have an answer. He just, mumbled something like, I don't know what happened to me. Okay. So it's true that, each of us are, capable of engaging in very, unsocial activities when we are part of a crowd, whereas individually we would, we'd not even think about all those things. So what is it that leads a group to engage in tasks which as individuals which we won't be joining in? Okay. So this is this emergent phenomena which occurs when you bring things together which individually you won't see in the component. Okay. And this is what makes network science so important. And as Anderson said, that at each stage, as you go up from elementary particle physics all the way to psychology and social sciences, at each stage you have entirely new laws, new phenomena, concepts and generalizations coming up which require a lot of creativity to uncover. So as he said, psychology is not applied biology, biology is not applied chemistry, solid state physics is not applied elementary particle physics. And so the reason why physicists are interested in networks is because it gives us a handle to understand how this emergence of new features appear at the systems level, features which don't exist at the level of the individual components. It's not magical, obviously. It's not like, so in the late 19th century and early 20th century, there was this school called vitalism, right? So it said that, living creatures cannot be examined by science because there is this vital force which, imbues them with science. So we say that that's not true, so you can see such emergence of new features occurring at things which are not even living. And so maybe all these features that we associate with this vitalism is actually not magical at all. They are just, features which are coming as a result of interaction between the components, where the components themselves do not exhibit this vital force. Okay? And so we say that emergence occurs in a network of interacting components where qualitatively different behavior arises, where this qualitatively different behavior from the individual component. And a wonderful example of this is the brain. So here the components are the neurons. You take a trillion neurons, wire them together in a particular way, and you get the human brain which is capable of giving this talk to you. Now, if you ask a neuroscientist, of course this neuroscientist is going to say, who says a neuron is simple? I am not actually even arguing that neuron is simple, but I think you'll all agree that compared to the complexity of the trillion neurons which is giving this talk, the complexity of a neuron pales to insignificance. And so that's what I'm talking about, that how do the interaction between these trillion neurons leads to the new complexity at the systems level, namely the level of the brain. So that's what actually the physicist approach to networks is all about. Okay, so I'm sure you have encountered at least classical mechanics and thermodynamics at some point in your education, right? Those things will be familiar to you. All right. So let me give an analogy of emergence from that. Okay. So when classical mechanics came about, its primary purpose was to understand what is the behavior of a single particle. Okay. So if you remember your classical mechanics courses, you're basically writing down how does a single particle behave under a certain force. Okay. So the first person to write down the set of laws to about how this particle behaves under forces is of course Kepler, and then eventually Newton put it in a solid foundation with his famous Newton's laws plus the universal theory of gravitation. Now the important point to note is that the relevant variables here are position and momentum. So we denote position as x and momentum as p. Now at about the same time that classical mechanics was developing, you also had the science of thermodynamics developing. Now unlike classical mechanics which deals with a single particle, thermodynamics is dealing with an Avogadro number of particles. Okay, 10 to the power 23 is so large that I can't even conceive of that picture. All right, the population of the planet is roughly a billion, right? 10 to the power, well, 10 to the power 9, right? So this is like 10 power 14. So imagine 10 to the power 14, which is like a 100 trillion Earths put together, right? It's such a huge number, right? But that's what thermodynamics is talking about. So many particles interacting with each other. So at this point, talking about position and momentum becomes meaningless. Imagine trying to keep track of position and momentum of, population of 100 trillion Earths. Okay, it's impossible. right? And so you don't even try. Instead, you deal with macroscopic variables such as pressure, volume, temperature. Okay. Now, can you actually talk about pressure, volume, temperature of a single particle? You can't, right? Doesn't even make sense. So, in a sense, thermodynamics and classical mechanics seem to have very little to say to each other. Okay. And just as you had Kepler coming up with the phenomenological laws, you had Boyle's law, Charles' law, Gay-Lucas law, and then eventually it was put in a solid foundation by Carnot and Clausius with their 3 laws of thermodynamics. And for a long time, the domain of classical mechanics and the domain of thermodynamics had very little to say to each other. Okay. Now, you might say, why do I even want them to talk to each other? The reason is something very funny occurs when you go from the world of classical mechanics to the world of thermodynamics. You have the emergence of the arrow of time. Anyone knows what is the arrow of time? Or what do you think is the arrow of time? Anybody? I mean, when I say arrow of time, what do I mean? This is something you must be all familiar with. Imagine taking a piece of chalk and I just throw it with enormous force on the ground. What will happen? The chalk will shatter, right? Will the opposite happen? So, like there are many shards of chalk here, they will just all come together, become a single chalk and jump into my hand? Very unlikely, right? And that's basically the arrow of time. Okay, that usually things tend to move such that the entropy increases. This is one of the fundamental laws of thermodynamics, right? However, if you look at each individual atom which makes up the chalk, it's all time reversible. Newton's laws are time reversible. There's nothing preventing each individual atom from going this way or this way. Okay. So if you look at it in terms of individual atoms, there is nothing preventing it from going this way, I mean falling from my hand to the floor, and then shattering, or coming together and then jumping to my hand. So the arrow of time is clearly something which is magically appearing when I go from the world of single particles. But when you put all the single particles together, suddenly you can only move from the past to the future. So if I show you a movie, and in fact there are many such movies, right? So I remember when I was a kid, there was a series called Satyajit Ray Presents. So there were these short stories that Satyajit Ray had written, and his son Sandeep Ray was directing a series of episodes in a television series, and one of them was about a scientist who had died and he had left behind a diary, and this diary had the usual like formula which will eventually lead to Nobel Prize if properly worked upon, and his friend was given the job of transcribing the diary, and the friend, of course being smart, decided that why not claim that I have discovered this, and he burned the diary. And then the climax of the story is that the friend is kind of working on his, the person who has died in his study, and then he suddenly finds that the grate in which he had burned the diary, the fire starts up again, and then the diary appears from its ashes, joins together, and basically the fire goes down and there's the intact diary. So this is basically to give you a ghostly element, because it doesn't happen in reality. So if you show it, that means that there is something supernatural going on. So how do we know it's supernatural? Because it's running counter to the usual arrow of time. So in fact there are many, Christopher Nolan for example, have any of you seen his movies? Memento for example. So Memento actually works by using this arrow of time forwards and backwards. So the reason why, if you look at the narration of that movie, it's a very, very simple revenge story. Okay. So a man who has lost his short-term memory wants to murder whom he thinks is his wife's killer. but he's manipulated by another woman to murder someone. And if you just showed it in actual chronological time, you'd think, oh, okay, one more of those revenge movies. So what's the big deal? But the reason why Memento became such cult hit is because he deliberately uses this forward and reverse time to show it. And the very fact that he's playing around with the directionality of the arrow of time makes it a classic. Okay, so film directors use this all the time. Okay, so the question is, where is this arrow of time coming from? Okay. So the arrow of time is an emergent phenomenon. Okay, so for a long time people puzzled about this until Boltzmann in the late 19th century came up with statistical mechanics to explain this. So he said that, look, what's happening is, yes, every individual microstate is reversible, but if you look at the total number of microstates which correspond to a particular macrostate, then the macrostate which has more microstates corresponding to it is much more probable. And so you will have basically a transition from macrostates which have fewer microstates associated with it to macrostates which have more microstates associated with it. And this is basically the entropy. Entropy is nothing but that how many microstates are associated with a particular macrostate. Yeah.
When you say that the individual particles are reversible,
yeah.
Like the physics of that is reversible.
Yeah.
But suppose if I have an individual particle far away from a body which is exerting gravity on it,
yeah.
It will go from like high energy state to a low energy state, right? But
yeah.
Left or right, so it will not go back to that far away place. So,
true.
Yeah.
Yeah, no, so what I meant was, if I reverse all the forces, okay, so basically in Newton's laws, you can put a negative sign over the entire equation. So now instead of, having an attractive force, you could have a repulsive force. So it's completely time reversible in that sense, okay. So, I could equivalently write down everything with a plus as with a minus. Okay, that's what I meant. Okay. So, so the reason why we have arrow of time is because the shattered chalk on the ground has more microstates associated with it than the one where I had the chalk in my hand, and so therefore it is possible that it can all come together, but the probability is so low that over the entire lifetime of the universe I will not see this happening. Okay, just as I'm sure you, if you have done a course on thermodynamics, I think this is one of the very favorite questions of when we set exams, is that what's the probability that all the oxygen molecules in this room would suddenly decide to clump together into this volume? They can actually, but what's the probability of this happening? Okay, extremely low. Okay, of course, if that happens, it will be a very unfortunate consequence, right? We'll all asphyxiate, right? But the probability of it is so extremely low that in reality it won't happen. Okay, that's because this is a extremely low entropy state. Okay, whereas all of them dispersed all around the molecule is a high entropy state. Okay, all right. So this is an example of why, or rather this gives you why statistical mechanics was first invented. And so it's not surprising that now when we want to understand why emergence, so we try to connect network, which is basically one way of thinking of emergence, with statistical mechanics, which was the science of emergence. Okay, so so statistical physicists initially used to work mostly with lattice systems. So lattice systems are very, regular grid-like systems. So, think of a very well-ordered city with block structure. So unfortunately, I don't know what's the equivalent in Ahmedabad, but in Calcutta there is this Salt Lake, suburb, which was a planned city. So it had, basically a block-like structure. So, okay, it's not exactly a rectangle, but it's like designed like this, and it has this grid-like arrangement. Okay, and not surprisingly, the blocks are all numbered AA, AB, AC, BA, BB, BC, and you are supposed to, navigate yourself very easily from here, because if you know that, so suppose you're in block AA here, and suppose you want to go to, I don't know, LF block over here. Okay, so you know that, how exactly you have to maneuver yourself like this. But typical cities actually, are not like that at all, right? So initially, when statistical physics tried to understand interactions, they were dealing with, well-ordered systems like this. So basically, you'll have the components arranged such that they will occur in the intersection points, and these roads would appear as the interactions, right? So basically a simple grid-like arrangement, and then you try to understand various properties. So one of them is this concept of percolation, or how do things spread by going from going across connected sites. So you cannot just jump across like this. So if I want to know how do I get from here to, let's say, here, I basically need to know, okay, how do I actually, go like this? And let's say, suppose some of these roads have been blocked off due to, people working on the streets or whatever. Can I find a connected path? So how many of these roads will have to be unusable before I won't be able to find a path from here to here? So questions like that. Now you might say, okay, who else but a mathematician would be interested in things? Well, can you actually imagine studying this percolation? So percolation originally arose because of an extremely practical problem. Anyone can guess?
Rainwater going to the
Sorry?
rainwater going to the bedrock.
Actually, it's a wonderful answer. That's not quite what I was looking for, but it's a wonderful answer simply because people who do petroleum exploration are very interested in percolation, because much of oil in sedimentary rocks is actually hidden in this interstitial layers of rocks. And so what they do is they inject water at extremely high pressure such that the oil is, ejected out. So this is a standard way of oil extraction, and those guys are very interested in percolation actually, because they want to know at what pressure they should inject water such that it displaces the oil and it comes out. Okay, so wonderful answer. So that's actually a very good practical example. So, but the actual practical example for why people came up with percolation was this was the First World War, and both the Germany and England were using poison gas against each other's soldiers. And so suddenly it became very important to devise gas masks. Now, if you have used mask in COVID, you know that the big problem with mask is how to have a mask which is thick enough to prevent the pathogens from getting into your respiratory system, and yet it has to allow air to go in. So you don't want to just keel over for lack of oxygen, right? So how do you design such masks? So people who were devising this gas mask very quickly realized that if you have, okay, so I'm going to draw a gas mask. Just imagine this is a gas mask. Okay, so this is the eye socket, this is the strap and so on, and this is the part where air is coming in, and you fill this with basically charcoal. Okay. Oh, today of course we use activated charcoal and so on. Now you pack charcoal to a very high density. So what happens is that this charcoal is actually acting as a mesh, and air molecules have to find a way through the gaps within this charcoal. So it has to find a way like this. Okay. Now the idea is that if you pack it tightly enough, the poison gas molecules, which are larger than air molecules, would be trapped. They simply won't be able to find a path. But air molecules, being small enough, would be able to find a path. Now the question is, what should be the optimal packing? Because if you don't pack it tightly enough, both air and poison gas molecules would go through. If you pack it too tightly, neither air nor gas molecules will go through. So you have to have some kind of an optimal packing. Okay? And that's how people started getting interested in this question of percolation. That can you find, so imagine that these crossroads are the ones which are not allowed to the poison gas molecule. Okay? So the question is, can you actually block all such shortcuts such that eventually the poison gas molecule is going to get trapped, but air molecules would find that many of these paths are actually open to it and would eventually be able to find its way to inside the mask. Okay? So that's this very, very practical problem which started off the whole field of percolation. And as you actually suggested, that even now percolation actually is used for lots of other practical exercises like oil exploration and so on. So you can do this on a lattice, but if you think a bit about it, actually there is nothing which says that this actually has to form a regular grid. So for example, in oil exploration, it definitely is not a regular grid. And so a better description would be a network rather than a grid. Similarly, if you look at random walks, okay, and random walks is actually studied for a whole lot of different things, like in message passing and so on. And you ask, okay, how long will it take for, let's say, a message to go from one particular point to another if it's undergoing a random walk? Again, this is normally, originally it was studied in lattices, but you can study it over a network. Similarly, you can look at diffusion. Okay. So again, in the case of diffusion, people started originally with lattices and tried to see how larger molecules would try to go through such systems. But again, if you really look at real systems, they don't look anything so regular. So a network would actually be a much more better description. Okay, and finally I come to another very nice example, which is synchronization of oscillators. Now again, you might think, okay, why would I be interested in synchronization of oscillators? So it turns out that our bodies are full of clocks. There's of course the heart, okay, but things like circadian rhythms, so suppose you need to wake up in the morning and I put you in a room which is completely dark, chances are that you'll still wake up around 9, okay, no matter how dark it is, unless of course you have gone to sleep after a hard partying at 6 o'clock. So what is this natural body clock of ours which allows us to wake up at the right time, even if you have, taken out all the cues, like no sunlight appearing, there's no alarm clock and so on? That's because our bodies actually have a variation in its gene expression which has a time scale of about 25 hours or 26 hours. Actually, it's slightly. We have a natural sleep-wake cycle. Now, it's a very interesting question. What would happen if you don't give anyone any cue as to when there is daylight and when there is night? What will happen to that person's sleep-wake rhythm? So people who go on space, they, for example, don't have any obvious cues, right? Because their spaceship is going around Earth, there's no obvious sunlight and so on. So for us, even if we kind of our sleep-wake cycle goes out of sync, there's still daylight outside to, for example, cue us back in to the natural sleep-wake rhythm. But people in the early 20th century were very interested to know what is the natural sleep-wake cycle. So they would do fun experiments like putting graduate students inside a room and taking out all the clocks, no windows, and from time to time meals would come, but all the meals are same, so you have no clue whether this is lunch, dinner, tea and whatever. And then the researcher, typically the advisor, would watch from a one-way mirror. So basically the student can't see out, but the advisor can see in, as to when is this person sleeping, when is this person awake and so on. So, it used to go like this. So let's call this the various days. Okay, so this is day 1, 2, 3, 4, 5, 6, 7, 8. So initially, of course, this was the period of activity and then period of sleep. So this is activity. Okay. And then, so it seems to be going, and then basically it's going out of sync, right? You still have a day sleep-wake cycle, but it's completely gone out of sync. That's because our natural body clocks are not actually 24 hours. It's more like 27 hours, okay? And every time people complain about me waking up at around 12 noon, I say, well, that's my body clock is, not really 24 hours, okay? So, so then, after a month or two, when the graduate student has had enough, the advisor would open the door, let the graduate student out, and then see how long it takes for the graduate student to go back to the 24-hour rhythm. Okay, and it's very fast actually, but usually, it takes sometimes, depending upon when that student emerges back into the sunlight, it may take a longer time for the adjustment to occur. Now, this experiment occurs naturally to all of us who actually fly from India to US or back. It's jet lag. Okay. So basically, we are slaved to the particular rhythm of India, and because of, see, previously when you had ships and you took several days to get there, your body naturally accustomed to it, because there was only a small slight adjustments and your body basically took care of this. But suddenly you are transplanted to a completely different time zone, and there are individuals for whom the body clock is completely, set, like goes wonkers, okay? And these people actually, have a very hard time getting out of jet lag. So trust scientists to come up with interesting experiments. So there was a scientist called Winfrey who decided to study this with the common housefly. So what he did was, he basically had this housefly undergo an artificial daylight-night cycle, and then he decided to suddenly give, during night time, a sudden jolt of bright light. Okay. The idea was that, is there a particular time in which I suddenly wake them up such that I can set their body clocks completely off? And he found that indeed there is actually a very critical time during which if you give them a bright jolt of light, after that they are no longer able to get back into their natural body clock. So they are in a permanent jet lagged state. So they basically go to sleep for a few hours, then become active for a few hours, go to sleep for a few hours. So this 24-hour or whatever, 27-hour rhythm or whatever is the natural body clock of Drosophila is completely lost. Okay, and this understanding led people to suggest that, look, maybe the cure jet lag is, for example, to give a proper dose of sunlight. So many people who are very veteran travelers, typically, senior scientists who travel a lot from US to, other parts of the world, would actually have this theory that, after I come to a new country, the moment morning happens, I just, go to the terrace and have a good dose of sunlight so that my body is set back to the natural 24-hour rhythm of that particular country. And, usually it works. And the science behind this is basically explained by Winfrey's experiments with this Drosophila. I won't go into the science because that's a very interesting science in its own right. But I just wanted to show you this example of how you can have oscillators. So, so the why did I get into the oscillators is that, our body is full of all these clocks, the heart, our genetic expression, then even longer clocks, like for example, the one which controls the menstrual cycles and so on. So these are all in some sense working in coordination. So how are they working in coordination? Obviously there's some kind of interaction going on. So people have been studying this for a while. So here what they have done is that they have taken a modern spin on the experiment done by Huygens. So they take a number of metronomes, and you can see that they deliberately set them ticking at completely different phases, right? They're not in phase at all. But over time, you'll notice that they gradually come into the same phase as each other. And the reason why this is happening is, of course, that there is interaction among them which is coordinated by this block. Okay, and that's the reason why you put them on soda can. If you didn't use the soda can, the vibration would be absorbed by the surface on which they are located. Okay, and now you can see that they're all in sync. Now this is but just a cheap version of what is happening in our body. Okay, our bodies have large number of clocks and they're all talking to each other. Of course, they are not in a simple linear arrangement like this. They are actually in a network, but the property is the same. I mean, they are somehow synchronizing. And what we really like to know is how the synchronization is happening over a network. So I just showed you a few examples of very good question. Yeah. So it turns out that depending upon the distance of the two clocks, they can either do 180 degree or 360 degrees. So 360 degrees is the same as in phase and 180 degree is anti-phase. So both solutions exist. Which solution you will get depends on the initial condition and the parameter values. Excellent question. So in fact, I can actually show using very simple mathematical arguments that under what conditions you will get 180 degree relation and 360 degree relation, 0 or 2, 0, pi, 2 pi, 3 pi, 4 pi, these are all solutions, and whether I get pi or 2 pi actually will give me anti-phase versus exact in phase. Excellent question, thanks. Alright, so so why networks instead of lattice? Because in reality, of course, this kind of things are very unlikely. Okay, most cities you will find, so I've been to old Ahmedabad once and got lost, and I realized that that's because it looks more like this. So there are like roads and then inner roads and warrens and so on instead of this. Okay, so a network is a better descriptor of this than this. Okay, so everything that I showed, the phenomena that you study in lattices can be studied in a networks, and that would be a much more accurate representation of reality than the grid. Okay, and so that's how networks became so popular. And this is just an example of in the natural world we see networks everywhere. And just to give you an example of the various scales in which we see networks, we see them right from the level of molecules. So this is a protein, and you can actually describe a protein as a network. Any idea how? Are you all familiar with in order to describe a network, as I said, you need to define two things: the vertices and the edges. So what are the vertices here? This is a single protein, right? The amino acids, or rather the carbon alpha atoms. Okay, yeah, but you're right. So those are the vertices. So for those of you who don't know, proteins, or may have forgotten, the proteins are actually chains of amino acids. Okay, huge chains. Okay, but they are not just like chain-like objects. So if you let them be, they just fold up, and they always fold into exactly the same structure. And that's very important, the fold into the same structure, because it's a folded structure which actually leads to the protein doing certain specific things. Okay, so you're right, vertices are the amino acids. What are the edges? Now, it's true that the carbon alpha atoms of the amino acids are bonded to each other with these double bonds. Okay, but this is actually not the interesting one. The interesting ones is what actually holds this three-dimensional structure together, and those are actually van der Waals bonds, van der Waals interactions. That's what allows us to understand the tertiary structure, the functional structure of the protein. Okay, all right. So if you are interested to understand the protein as a three-dimensional folded structure, you need to describe the interaction in terms of the van der Waals interactions. Okay, so knowing these two, you can actually describe the protein as a network. And then as you go further up the scales, at the level of cell, you've got the intracellular signaling network. So these consist of a series of proteins, then calcium, the second messengers and all that, which actually allows the cell to know what's happening outside and take appropriate action. At the level of organs, you have neuron, the brain for example, where the vertices are the neurons and the edges corresponding to the synapses. At the level of populations, where you're, for example, you might be interested in epidemics. So here the individuals are, of course, human individuals, or for that matter animals or whatever, and the interactions are like, actually them coming together so that the pathogen can go from one individual to another. And then finally, at an even higher level, you can look at ecologies as networks where the nodes are various species and the interactions are basically who it's who, the trophic relation. So you can describe food webs. And in each of these systems, you can ask questions of stability, robustness, how quickly they can adapt to changing environment and so on. So looking at other examples of, so those were all examples of biological network, but from your perspective, what could be more relevant are things like social networks. Okay, so in social networks, you could have the number of individuals vary from anything between 3 to population of the planet. Okay, so 3 is actually the minimal number and not 2. Okay, because sociologists, for example, are interested not so much in the diet as what happens when one diet tries to interact with another diet. Okay, so always the most the simplest non-trivial network is the triad, and I will in the very last lecture talk about how this triad can have various different relations so that you can actually see the universe of social relations in just a triad of relations. Okay, famous love triangles, right? Grist of all Hindi movies, right? So you can actually study a lot of network science just by looking at triadic relations. So that's why it starts from a triad, and you can look at the entire Earth's population as like a large social network. And here the links are social interactions. Now there's a before the internet, before the social media and so on, it used to be pretty much physical interaction. Who do you actually know? And that used to be pretty small. So there are some arguments that at most we can have 150 meaningful relationships. Okay, and there are practical reasons why. So you can have a lot of friends in Instagram and so on, a lot of followers, but you may not know any of them. Okay, so to actually have friends, you need to invest, right? So I have to at least call them once a while or send them like Happy New Year or something in order to retain the friendship. Okay, otherwise we just stop being in touch. I mean, I'm not in touch with most of my classmates in school, for example, because I didn't have time to talk to them a lot and so on. So now if I suddenly turn up somewhere, they will say, what does this guy want? There must be something he's up to and so on, right? So in order to retain friendships, you need investment. And since we have finite time, we can only invest in a few relationships at a time. And so that's how this 150 came up. But there are other reasons, I'll come to that. And typically here the interactions mean that there's some way in which A knows B. This knowing may be through social media, this knowing may be through actual physical interactions, And so this can be measured, for example, the duration of phone calls, the frequency of emails, how many posts of someone have you liked, or it could be just physical proximity. Or if you are in the market and you're looking at agents, do they frequently trade with each other? Okay. And the other very important point is that the relations are not all equally strong, and so you can characterize them by being weak or strong. So you can actually associate a strength of these interactions. So I promise that I'll talk about this 150 business. So actually this is something that Robin Dunbar came up with, and he said that the 150 is coming up because he argued that we have large brains, or primates have large brains, not for doing science or math, but to negotiate our very complicated social worlds. Okay? So primates live in very densely connected social groups. So if you are familiar with some of the work done on, let's say, chimpanzees or gorillas or orangutans, you would know that it's a very, very complicated social world that they live in. So if you're the alpha male, life is very pleasant for you. You get all the food, all the women, everything's up for grabs for you. Okay, but if you're not an alpha male, life is tough, right? So of course you want everything that the alpha male has, right? You want food, you want women, and so on. So what do? You try to see when is the alpha male's attention diverted, and then you try to grab. Okay, and you engage in various kinds of subterfuge. Like for example, you give a warning call that the leopard is coming when of course there's no leopard, and then the alpha male kind of goes around to investigate. You quickly have a nexus with one of the women. And similarly for food, I mean, one of my collaborators is a primatologist working at National Institute of Advanced Studies, and he's actually seen this in action in Bandipur forest, where he says that, so he works with macaque monkeys. He says this macaque monkey is, he's seen a bunch of ripe bananas, but he's deliberately looking the other way. Bandmates think that there's something very interesting going on in the other way, and then something happens and the others kind of go there, and then he quickly swipes this ripe bananas for himself. And so you have to kind of weave a very fine line between getting stuff for yourself and not getting beaten up by those who are superior up the chain. So you think humans are hierarchical? Just try being a macaque. Macaques are so strongly hierarchical that everybody knows their place. Okay, so if you are like down the chain, you don't actually approach someone who's higher up the chain. Okay, you wait for that other person to come to you. If you try to do the other way, the next thing you know, you're on the floor and getting bashed up. Okay, so they develop brains so that they don't get bashed up all the time, and yet do not, go basically without food or woman either. So you got to know when you can get your way and when you should, stand back. And the size of your brain actually correlates beautifully with the size of the band, okay, or the size of the neocortex rather, not the brain properly. So he has this thing that if you look at the neocortex to brain ratio, and if you look at the mean group size, you can see that there's a very, very strong correlation, and humans is somewhere here. Okay, so humans are not very different from primates when it comes to brain size to neocortex size, and from this he kind of developed this kind of a extrapolation that given that our neocortex ratio is about 4, so then the natural group size is something like 150. Okay, and the way he thinks of this 150 is like this, that the strengths are not all the same. So this is your closest relationships are about 5, then you have about 15 good friends, 50 friends, and then 150 meaningful relationships, which means that these are people you are in regular contact with. Okay? Now, interestingly, you can actually study this in fictional worlds. So, for example, someone came up with the social networks in the 6 novels of Jane Austen, the 6 complete novels, and you can try to, look at the properties of such networks, and you find that they kind of reflect, many properties of real social world networks. But they are of course much simpler than those observed in reality. So once I had this theory that the reason fictional and especially the social networks that you see in movies are way simpler than actual social networks is because you have had an entire lifetime to understand your own social network. When you go to see a movie, you have barely 2 hours to make sense of the social universe. So obviously the social networks in fiction would tend to be much simpler. But there are of course exceptions. So you can see, for example, if you look at Shakespeare's plays, you can see that as he's becoming older and older, so if in the earlier plays the social networks tend to be very simple. In his later plays, the social networks are becoming very, very complex, almost mirroring reality. So you can see he has mastered his art to the point where he can actually convey the very complex social network while still making it a play which you can understand. Okay. So these are fun things to do if you are collaborating with a literary scholar. So it falls under the rubric of what are known as digital humanities. So this is this hypothesis that do fictional social networks necessarily need to be simpler than those in real life. And so once I was talking about this in a network school, and I said, I wish someone would do this for Mahabharata. Ramayana is a way too simple network actually. But Mahabharata has this stories within stories within stories, and it would be really interesting to see how we can actually represent it as a network. So someone actually started working on this, but then being a graduate student, I think his advisor said, are you serious? You think you're going to make this into your PhD? And the guy said, I'm sorry, my advisor is not going to allow me. So anyway, so this is still an open problem, and I'm always trying to tell people whenever I meet them that, I really wish someone would do this. Okay. So in case any of you are interested. Okay. And for people who are more tuned in with the latest stuff, this is the Marvel Cinematic Universe. Okay. So, based on all the movies which have come out, people have actually connected them, and so some of them you can see like Iron Man, Captain America, Thor, individuals like I think Pepper Potts is here, who's of course not a superhero, and so on. Okay. Now, why do all this? Okay, so you might say, okay, it will get me a paper in IEEE proceedings. Maybe I'll even go into IEEE conference. But is it of any use? Okay. But for one thing, it actually gives you a handle to understanding certain historical puzzles. Okay, and which might have ramifications for reality also. So, for example, it can help explain why did certain families or certain individuals become so powerful. Okay. Now you might say, okay, so what's the big deal? We know that I won't name them, but certain industrial families in India are very powerful because of their closeness to the power centers, right? What's the big deal? Okay. But how did they get there? Okay. Now, yes, once they have gotten to that position, it's pretty obvious. Right? There were so many other competitors, right? There are other industrial families also. Why didn't they get to that position? Why did these people go there? So, someone called Paget, working with today's data is very difficult because most of the data is confidential. He had to work with data from the 16th century Florence. Okay, so those of you who watch Netflix regularly might have seen this series, The Medici. Anyone? Yes, no? No one has seen it? Oh, great. Okay, good. So, so then you're familiar with, the story that there was this guy called Cosimo Medici who actually set the ball in motion so that his family becomes the most powerful family. So the Florence was nominally a republic. Okay, so there are no kings. It's ruled by a council, the Signoria. Sorry, am I confusing it with Venice? Anyway, it's ruled by a council which has representative from the major families. Okay, and these families are mostly involved in banking and other kinds of trading activities. So the Medici was like one of the many such families. Okay. However, Cosimo, being very far-sighted, played here by Dustin Hoffman, managed to position his family such that within 200 years, the Medici actually became the kings of Florence. Okay? Literally, they turned it into a kingdom. Okay? The question is, how did they manage to? Because they were not the most powerful dogs in the manger. So there were other very powerful banking families. In fact, the Strozzi family almost had the Medici killed and replaced them. Nevertheless, they survived and eventually took over. And you might say, okay, it's just a one-off, maybe there were historical accidents and so on. So if you look at the Netflix series, for example, you would say, oh, big deal. I mean, it's just a series of one accident after another. As someone has said, history is just one damn thing after another, right? So it's just accidents. But Paget said, maybe it's not just accident. Okay?
A wise man lives with a purpose. A foolish man lives for himself. One day, when I'm gone, you will be head of the Medici family, and you must lead us.
A new world is here. A world of business and trade. A world where men are rewarded for their ideas and initiative. A world where if you are born poor, it no longer means your children must remain poor.
Are you sure there isn't anything you wish to confess?
Medici, come out here! People have seen the truth. There's only one answer to the charge of treason. Death to the traitor.
Exile.
I couldn't lose you.
If I have lost Florence, the Medici are ruined.
I did everything I could to secure your return. Was it such an unforgivable treason to have saved your life?
The city stagnates. For the new leaders to rise, the old must fall.
This doesn't erase the past, Medici.
Do not force my hand.
Everything I have ever done has been for you, for Florence, for the greater glory of God.
Okay, so this is, the, what do you call it? The Netflix view of the rise of Medici. And I'm told the series, how do you like the series? Is it good? I actually never managed to go beyond episode 1. Okay, good. So maybe you should try watching it, okay? But the reason why I brought it up was Paget took a very, non-Netflix way of approaching this. And he said that, can you actually explain why the Medici rather than some other of the more powerful families became so powerful? And what he did was he started connecting, mapping out the social network of the Medicis in terms of marriage relations. So marriage relations over here are these pink ties, business ties, that is, you actually have business relations with these families, green ties, and also patronage ties, which I'm not showing here. So patronage meant that if you wanted to be in the council, you needed to get, reco letters. Okay, so, and reco letter not from your father. You need a reco letter from the heads of the other like 3 other families, So who is writing patronage letters for whom, right? Now, if you notice something, and Paget actually made this very important point, the Medici are not central in any individual network. So in the marriage network or the business ties network or the patronage network, it's not like they hold a very special position. But if you collapse all these networks, you find that they are becoming center. So in other words, they are very strategically doing this marriage relations, business relations and patronage relations such that they're managing to tie up all the families. So if the Strozzi want to talk to, let's say, the Pazzi, they have to go through the Medici. Okay, so they are basically acting as the exchange center. All right, they are becoming central not because of their position in any one particular network, but across the three networks. And this was done by strategy. This is not just by accident. This is what Cosimo was doing. Okay, so Cosimo made pretty sure that you don't necessarily have marriages with the families with which you are holding business ties, because you already have business ties. So I will have marriage relations with those families which I'm not having direct business with, and then I'll write patronage letters for those families which I'm not connected either through business or through marriage. So in this way, I'll make sure that all the families are tied to me, and any family trying to connect with any other family has to go through me. Okay, so this is called network leveraging your network power. And Cosimo, without knowing any network science, managed to figure this out. Okay, and so if you are interested, you can try to see whether the same thing is true for some of the business families in India today. Okay, and of course you are very familiar with networks as they apply in technological networks like in transportation, power transmission, information, and so on. And so what is actually fascinating for me is that the history of graph theory or history of network science actually dates way back, like in the time of Euler. So network theory is, started when Euler tried to solve this very simple problem, that if you look at the city of Königsberg, which is now I think the city of Kaliningrad, then there were these 7 bridges across the river Pregel, and the question that people often asked was that, can you actually find a walk through the city that would cross each bridge once and only once? And so you can try doing this by trial and error, and you won't find something, but then you think, okay, maybe I've not tried everything else. And Euler had a very, very simple solution to this. He simply said that, well, any path which can do this must enter as well as exit each node as it passes through, except the first and last nodes. This implies that at most 2 nodes in the network will have odd number of connections for such a path to exist. And so you can count this. So this is the network representation of this map. So A, B, C, D are the various land masses, and the bridges are these connections. And you can quickly count that all 4 nodes have odd number of connections. So this has 3, this has 3, this has 3, and this has 5. And so this says that you cannot actually have a solution of the original problem. So you cannot find a path such that you will go across all 7 bridges once and once only. So this is actually what is believed to have led to graph theory, and from there you have come a long way, where the great innovation which led to Google was how do you search the World Wide Web. So the number of web pages have increased enormously from 91, and the question of how do you actually find, so people who initially started the World Wide Web thought that this won't expand beyond a particular size, because they said that any useful piece of information, you won't be able to find it once it goes beyond a certain number of pages, because trying to find the relevant thing is like trying to find a needle in a haystack. Until, of course, Google figured out a wonderful technology for doing this, and what they did was actually use graph theory, right? So how do you measure the importance of a node? Well, one is to just simply ask how many other nodes does a node know, and this is this idea of degree, okay, the number of connections. But the idea of Google's PageRank algorithm is that it's not just how many you know, but who you know. So the importance of a page is determined by the other important pages you are linked to. Now you might say, okay, this seems like a circular definition, right? Because importance is itself defined in terms of the definition. But you can do it using linear algebra, and so you use eigenvector centrality. It's quite late, so I won't go through this. Suffice it to say that I can describe this in the next session if any of you are interested. So instead of that, I will just say that the same thing can be done by simply randomly surfing the net. So this is the so-called random surfer model, where you just basically go from one page to another linked page, and you keep doing this, and the score or rank of a page will be related to how frequently you are coming back to that node. So if you are interested in this, I suggest there's a very nice video in YouTube which actually shows this using nice visualizations, and I'm just basically going to end by just today, this particular lecture by saying that networks is like just the tip of the iceberg. So you might say, okay, networks are mostly looking at pairs of relations, but why not looking at triadic kind of relations, where the triad is defined not just by A to B, B to C, C to A, but rather how the triad as a whole relates to each other. So I'll give an example. So Amit and I have a some relation, and let's say Amit and one of you has a relation. Now when you are talking to Amit and I approach, the entire conversation might change simply through my presence. And that is something you cannot explain using networks, because these are purely dyadic relations. It says that the fact that I am there should not affect your relation with Amit. Okay, it's not a very good analogy, is it? Okay, imagine something like this. You have a good friend and you have another good friend. Okay, and now as so happens you are cribbing to this one good friend about that other good friend. Okay, and then that good friend just saunters along, and suddenly your conversation changes to the weather is like very wet and so on, right? And so this is something that proper network can't handle, because it says that your relationship with this particular good friend should not be at all affected by whether that other good friend is present or not. So this is what I mean by having relations which cannot be explained by pure networks. So this can only be handled by hypergraphs which look at such higher order relations, where the relation between A to B can be modulated by the presence of C or D or E or whatever. So hypergraphs is of course something which is studied a lot by many computer scientists, but unfortunately it is not yet so commonly used in analyzing actual networks. And the other big thing is this multi-layer network. I mean of course multi-layer networks is something that Paget already looked at when he looked at marriage relations, then business ties and patronage relations. But this is only becoming common over the last 10 years or so. And I just give one example of the cell, where you can look at a whole number of interactions like protein-protein interaction, metabolic networks, gene transcription, cell signaling, and you try to understand how all of these are actually working together. So the links are all different across these different layers, but the nodes may be same, and you need to understand how these networks are all working together to create a meta network. Okay, so with that, let me end by just giving you a list of some introductory papers and books if you're interested of digging further in this perspective. So the best book I know of as a textbook is this book by Newman, Networks and Introduction, which is now in its second edition. If you are interested in a bit of the history of it, the dynamics process like epidemics on networks and transport on networks actually has been dealt very well in this textbook, Barat, Bartholomew and Vespidani. And if you are interested in more the application of networks to biology, Uri Alon's book is nice. Among papers, I quite like Newman's review, but if you are already reading the book, these are all redundant. And I also like reading popular books. So one of the best popular books on networks that I know of is Duncan Watts' 6 Degrees. So it's a very chatty kind of book where he gets into like how he came up with with his supervisor Strogatz on this concept of small world network, but he also talks about networks in general and so on. And of course, there's also another book by Barabashi called Linked, the New Science of Networks, which is slightly older, but also looks at the early days of network science. Okay, so I will end by giving you an assignment. This is called the 10 Bridges of Chennai. I'm sure this will be very simple for most of you. The idea is like, this is Old Madras. There are 4 land masses, A, B, C and D, which are separated by waterways. They are linked by 10 bridges, and I want you to basically draw a graph representing the above by showing the land masses as vertices and the bridges as edges. Then what would be the corresponding adjacency matrix? What is the average path length in the network? I understand that you've all done path length, so this should be easy exercise for you. And then the last question is it possible to find the Eulerian path? That is, can you find a path across these bridges so that you pass them once and once only, but you have to go through each of these bridges. All right? And if the answer is yes, you have to give such a sequence, like what is the sequence in which you will pass the bridge, and if no, you have to provide the reason why there may not be such a path.